Hi, today we're going to solve a differential equation, but not in the classical way. The differential equation we have is y prime equals x times y, and by ordinary methods, that's really quick and easy to solve. However, we're going to solve this assuming that it has a power series solution. Now, why would we want to find a power series solution? Well, sometimes differential equations can be difficult to solve. Well, they often are very difficult to solve. And the solutions aren't often in terms of trigonometric functions or exponential functions. So sometimes we hope that there's a power series solution and we try to find it. So let's see how we can tackle this. A power series would be given by y equals a naught x to the 0 plus a1x to the 1 plus a2x squared all the way up to the nth power of x with these coefficients a naught, a1 all the way through to an. If we were to differentiate each of these term by term, we would obtain the following. Now let's keep a pattern. The exponent would come down and multiply by the coefficient. The exponent would come down and multiply by the coefficient. The exponent would come down and multiply by the coefficient. All the way to the last term. The exponent would come down, multiply with the coefficient. And if we try to compactify these in summation notation, up here, we would have this. And for our derivative, we would have the following. However, notice this first term in this series within our derivative is just 0. So really, the amount of terms we have here is one less than what we have up here. So we could start our counter at 1. Now, assuming this is the solution, that this is our function y we're looking for, we can go back to our differential equation and write it as the following. Y prime minus xy equals 0. Substituting y prime, this, right here, we have this minus x times y, and here's our function y. Equals 0. Okay, good. Well, this x can multiply and get absorbed in here. And what we have is the following. If we look at the right-hand side of our equation, we have a constant term of 0. If we look at the left-hand side, do we have any constant terms? Well, in this summation, if we were to expand that out, k starts at 0, which would make the smallest power of x here x to the power of 0 plus 1, or x. So there is no constant term within this series. But over here, in this series, When k starts off at 1, the smallest power of x that we have here is x to the power 1 minus 1, which is x to the power 0, which is 1. So when k is 1, we do have a constant term. And so that constant term must be identical to the constant term we have over there. And all the other non-constant terms, all their coefficients have to match the coefficients on the right-hand side of all the other powers of x. But we have no powers of x on the right-hand side. So let's see what we can do with this. Let's extract the term containing or generated from k equals 1. When k equals 1, the term that comes out is 1 times a sub 1 times x to the 0, or just a sub 1. Then the rest of our summation continues on from 2 to infinity. And so we have this minus what we have in pink. Equals 0. And what we'll do now is pull a little move. Let's drop this counter down by 2 so that k starts at 0 and so that it matches this counter. But when we do this, we'll have to adjust what we have here for k. And if we bring this down by 2, we're going to have a k plus 2 here, k plus 2 here, and a k plus 2 here, making this exponent k plus 1. So now we have a sub 1 plus the sum from k equals 0 to infinity of k plus 2 times a sub k plus 2 times x to the power k plus 1. And we subtract off our sum in pink. Okay, well, why did we do that? Well, because now we can take these two summations together and group them into one summation. How would that look? Well, we have a sub 1 plus the sum from k equals 0 to infinity of, okay, well, we'll factor out an x to the power of k plus 1, leaving us with this quantity right here, k plus 2 times a sub k plus 2 minus this quantity here, a sub k, with this x to the power of k plus 1 factored out, equals 0. Okay, great. Now, as we said before, this left-hand side has a constant term of a1, and the right-hand side has a constant term of 0. On the left-hand side, all these coefficients of our powers of x, well, they have to be 0 because we have no powers of x on this side. So what we can say now is the following. Number 1, a sub 1 is 0. And secondly, this quantity is also 0. But now this, we can obtain the coefficients recursively simply by doing the following. A sub k plus 2 equals a sub k divided by k plus 2. And so let's make a list of the first few, maybe 5 or 6 coefficients. So we'll make our list over here of our coefficients. Okay, so when k equals 0, we have a sub 2 equals a sub 0 divided by 0 plus 2, or 2. When k is 1, we have a sub 3 equals a sub 1 divided by 1 plus 2 is 3. When k is 2, we have a sub 4 equals a sub 2 divided by 2 plus 2 is 4. But a sub 2 is just half of a naught. And if you take half of a naught divided by 4, that's an eighth of a naught. For k equals 3, we have a sub 5 equals a sub 3 divided by 3 plus 2 is 5. But a sub 3 is a third of a1, and a third of a1 divided by 5 is a 15th of a1. And for a couple more, when k is 4, we have a sub 6 equals a sub 4 divided by 6. But a sub 4 is an eighth of a naught, and an eighth of a naught divided by 6 is a 48th of a naught. And we'll do one more here for k equals 5. This tells us that a sub 7 equals a sub 5 divided by 5 plus 2 is 7. But a sub 5 is a 15th of a1. And a 15th of a1 divided by 7 is 1 over 105 of a1. Okay, good. So now we have a sort of pattern, or at least we can see what some of our coefficients are in terms of a naught and a1. So having seen these coefficients now, let's go back and put them into our power series here, our solution to our differential equation, and look for what else we can obtain from that. So let's go to our next board. Okay, here we are now back at the next board, and let's see where we left off. Our power series solution is represented by this, and we have coefficients a0, a1, a2, etc. And we found the first 7 coefficients in terms of a0 and a1. So let's take what we have here in blue and take what we have in pink and combine the two. In our power series, we have a0 x0 plus a1 x1 plus a2 x squared plus a3 x cubed plus a4 x to the 4 plus a5 x to the 5 plus a6 x to the 6 plus a7 x to the 7, etc. And here we can sub in all of our coefficients. Well, we have a0 and x to the 0 is just 1, plus, now we have a1, which is 0, times x to the 1, plus a2, which is half a0 x squared, plus a3, which is a third of a1 x cubed, plus a4 is an eighth of a0 x to the 4, plus a5, which is a 15th of a1 x to the 5, plus a6, which is a 48th of a0 x to the 6, plus a7 x to the 7, and so on. Well, we need to find a0. So what we'll do here is we'll factor out a0 from the terms containing a0. And that leaves us with 1 plus half x squared plus an eighth x to the 4 plus a 48th x to the 6. and so on. Plus we also have the terms containing a1. So we'll factor out a1 from those terms. So a1 times 0 plus a third x cubed plus a 15th x to the 5 plus 1 over 105 x to the 7 and so on. Now from our initial condition, we see that f of 0 equals 2. So when x is 0, y is 2. So let's use that fact. When x is 0, y is 2. Well, okay, we can substitute 2 right here equals a naught times 1 plus, well, when x is 0, we have 0 plus 0 plus 0, etc. And we see that our powers of x are increasing by 2. So we'll always get zeros here. Plus a1 times, well, same thing. When we plug in 0, we get zeros all throughout. So 0 plus 0 plus 0 plus 0, etc. So this entire term right here is 0. And over here we have 2 equals a naught times, well, 1 plus a bunch of zeros is just 1. So a naught times 1 is just a naught. So we now have a naught. And so since we have a naught, we can go back to our equation here and sub those values in. And we also know from above that a1 is 0. So all of these terms here containing a1 will vanish, leaving only the even powers of x behind. So now, let's look at what our equation looks like once we substitute in the rest of our values. Let's go to the next board. Okay, here we are at the next board. So let's see what we had. a1 is 0. And we saw that a naught is 2. So our power series becomes 2 plus x squared plus a quarter x to the 4 plus a 24th x to the 6, etc. So this in fact gives us our power series solution to our differential equation. Of course, in solving a differential equation, we would like to find the function y, which satisfies this. The derivative of y equals x times the function y. And so here's the function. Now, of course, that was a lot of work. And like we said at the beginning, this is not something you often see. But to get a taste of how this works, we picked a simple example. Sometimes a power series solution does come in handy when you can't find a solution in terms of trigonometric or exponential functions, some of the more elementary functions. But let's also see what we would obtain if we solve this with more conventional methods. So, given that y prime equals x times y, we can write this as dy by dx equals x times y. If we separate our variables, we end up with dy over y equals x dx. Well, if we integrate both sides, we obtain the following. The integral of 1 over y dy is the ln of the absolute value of y. And on the other side, the integral of x dx is just half x squared plus a constant of integration. If we take a power of e on both sides, then what we obtain next is the following. E to the power of ln of an argument is the argument. And over here, what we can write is e to the power half x squared times e to the power c. Multiplying these powers, since they have the same base, these exponents would add. So this is equivalent to this. Okay, well, this e to the power c, we can just call it a constant, let's say a. And so what we obtain now is that the magnitude of y equals a times half e to the power half x squared. Using our initial condition, f of 0 equals 2. So the magnitude of 2 here is 2. And that would equal a times e to the power of, well, half times 0 squared is 0. And so e to the power of 0 gives us just 1. And so that tells us that that constant a is just 2. And since that's positive, and this power of e is always positive, we can scrap the absolute value bars and say that our solution is y equals 2 times e to the half x squared. Now, is that solution the same as the power series solution that we obtained up here? The power series expansion of f of x equals e to the x is just the sum, as k runs from 0 to infinity, of 1 over k factorial times x to the k. In our case, we have half x squared as our exponent, so that gives us the following. F of x equals e to the power of half x squared, which would mean if we take this series here and expand it out, we would get the following terms. When k is 0, 1 over 0 factorial is 1 over 1 or 1 times x to the 0, which is just 1. Plus, when k is 1, we get 1 over 1 factorial, which is 1, times half x squared to the power 1. Plus, when k is 2, we get 1 over 2 factorial, which is a half, times 1 over 2x squared to the power of 2. And so on. Now, what does this reduce to? Well, this just stays as half x squared. This here, we have a half x squared squared, which is a quarter x to the 4, but divided by 2. That's an eighth x to the 4, and so on. But remember, we also have this factor of 2 in front. So if we put this here and multiply all of our terms by 2, we get a 2 here. A half times 2 is just 1. An eighth times 2 is just a quarter, and so on. So if we compare this solution, 2 plus x squared plus a quarter x to the 4, etc., that matches here, 2 plus x squared plus a quarter x to the 4, etc. And so there we have it. We've solved the differential equation with a power series solution. We've compared it to a more standard solution. And that's all. Thanks for watching.